My name is J.Trainer from Temple University in Philadelphia. I work in the group of Maria Averone, and today I'll be discussing a topic that's a little bit different from the superconducting talks we've been hearing, and that's the electronic properties of few layer molybdenum disulfide films. After a brief introduction to the material, I'll discuss our scanning, tunneling, microscopy, and spectroscopy results, looking at the role of the van der Waals gap on the electronic properties of the material. And then I'll move on to our recent investigation of applying kind of a macroscopic strain on the film and then measuring the local lattice deformation and the effect on the band gap. Okay, so molybdenum disulfide belongs to the transition metal dichalcogenides. These are layered materials with a structure shown here. These materials exhibit strong in-plane bonding but have a weak kind of van der Waals interlayer coupling, which allows for the easy exfoliation or synthesis of single monolayers. Molybdenum disulfide is a semiconductor, and so it is already advantageous over graphene when making certain devices such as transistors that require a band gap to have high on-off ratios, and single-layer devices have already been made with impressive metrics. In the bulk form, this material has an indirect band gap that transitions to a direct gap when thinned down to a single layer. The magnitude of that gap falls within the visible range, so this is an attractive material for optoelectronics. In addition, being a van der Waals material, it allows for kind of the stacking at arbitrary crystallographic orientation. Also, you don't have to worry about the lattice mismatch necessarily. So heterostructure devices can be made that have who have properties that differ from their parent compounds. And perhaps the most popular example of this is the recent discovery that twisted bilayer graphene at the magic angle of 1.1 degrees exhibits superconductivity. And lastly, like graphene, molysulfide is very strong in plane, but has a low out-of-plane bending rigidity, which allows it to be bent to high degrees without breaking. It's been measured to be able to withstand tensile strains up to 11% without rupture, which of course make it an attractive candidate for these next generation flexible electronic devices. So before I get into our tunneling results, I want to point out and acknowledge our funding and collaboration. This work was done under Temple's EFRC called the CCDM, and it was a collaborative effort through many different universities, many different people who I will identify their contribution throughout the talk. So for example, the films were grown in the group of Xiaoxing Shi at Temple University. This was done by ambient pressure chemical vapor deposition, which yields highly crystalline films of single to few layers that tend to grow in discrete one monolayer thickness steps. These films can then be brought into the UHV-STM at Temple University, the low temperature UHV-STM. The surface is prepared, and then we can do tunneling measurements. I won't necessarily introduce STM after Professor Rodachev's lectures, but I will echo that the tunneling DIDV is proportional to the density of states material. And so we see on this material a semiconducting spectrum where the magnitude of the gap changes with the thickness, specifically going from 1 to 2 monolayers, the valence band edge shifts. So we turn to our theory collaborators at Northeastern University in the group of Arun Bansal, who modeled the tunneling spectroscopy and found results consistent with our measurement. They also were able to calculate an orbital decomposition, finding that in the multi-layer system, so in the monolayer system, there's a direct gap at the K point, but in the multi-layer system, the top of the valence band edge is found at the gamma point, And the orbitals responsible for the states there tend to be the sulfur and the molybdenum, dz squared. And this has been found to be due to a overlap of the interfacial sulfur PZ orbitals, which shift this valence band edge up. And this is consistent with our tunneling measurement. In addition to this thickness dependence, we also studied the dependence on the crystallographic orientation of the single layer molybdenum disulfide with the graphite. And with different crystallographic orientation, we find an array of moire patterns with different moire periodicities that depend on the orientation. We found, however, that this moire periodicity doesn't strictly adhere to the geometrically defined curve here, which is just basically the beating pattern between the two lattice parameters as a function of the angle. We found that this result has been seen also in graphene that's been grown on different transition metal surfaces, where the film will tend to relax into a lower strained, or rather a more energetically favorable orientation, as some of the orientations have kind of a high energetic cost. We measured the tunneling spectroscopy on each one of these rotations, and we found that the band gap doesn't necessarily reduce monotonically as a function of the twist angle like we initially thought, but the behavior mimics that of the Moire lattice constant, where we see at small Moire lattice constants we have a smaller gap, and larger Moire lattice constants we have a higher gap. So again, we turn to our theory collaborators in the group of Room-Van-Ciel, who model this system first with the film and the substrate crystallographically aligned, and then at a maximal angle of 30 degrees. And they find that the band structure doesn't necessarily change by just rotating the two systems, whereas we find, of course, that we have a dependence on the gap with the rotation, but more specifically with this Moire lattice constant. So instead, if they model the system by changing a little bit the distance between the film and the substrate, instead they find that there's a shift in the valence band edge that reduces the gap with this enhanced interaction. In addition, with our tunneling measurement, this implies that with a smaller Moire lattice constant, this means that there's a higher density of coincident lattice positions between the sulfur and the carbon atoms. And this higher density of coincident atomic positions indicates that there's a larger interaction between the film and the substrate, and vice versa. When there's a larger Moire lattice constant, means there's a smaller density of coincident positions and therefore less of interaction, leading to a larger band gap. Okay, and with the remaining time, I want to discuss our recent results on straining the film of molybdenum disulfide, which of course has applications in strain engineering, among other things. This work was done in collaboration with SOLA at Argonne National Labs Center for Nanoscale Materials. And the idea was to take the single layer film on the substrate and to bend the substrate. And in order for this neutral plane to maintain the same length, the surface plane would have to undergo this tensile strain. And this would be then transmitted in principle to the film. And because molybdenum disulfide has a positive Poisson's ratio, you would expect then a normal compression in the direction parallel to this bending axis. So utilizing this geometry, we can define a nominal strain that should be found on the film that's related to the substrate thickness as well as the radius of curvature that we apply. So to this end, we developed and built a sample holder that's conducive to STM and can hold substrates with different radii of curvature and therefore different strains to do tunneling measurements on. And this geometry, we can achieve strains of up to 4.9% nominally. So the novelty of using STM as opposed to a photoluminescence study to look at the optical gap or the Raman spectroscopy is that we wanted to correlate the actual atomic scale deformation with the change in the density of states. And in order to do that, we use the so-called Lawler-Fujita algorithm, which basically says that the atomic resolution that we see in STM can be mathematically kind of displayed as just a perfect periodic lattice plus some kind of displacement field U. And so if we're able to use this formula and kind of extract U, we can find, after calibrating, of course, the piezos, we can find the displacement field, which should be related to the strain. So in practice, how we do that is we Fourier filter selectively the atomic lattice, and then we compare each atomic position to where they should be compared to the ideal lattice, and extract a displacement field at each atom. And so we can do this across the scan area in both the x and the y direction, and extract the strain in x and the y as just the derivative of the displacement field. So on our nominal strain of 0%, just a flat sample, we find very low strains, less than 0.3%. If we do the same thing on a nominal strain maximally bent sample of 4.9%, we find instead that we have a significantly higher strain in X of 2.6% approximately. And we have then a compression or a negative strain of about negative 1% in the Y direction. So the scanner is oriented, or rather the sample is oriented to the scanner such that the fast scan, or the X direction, is in the tensile strain direction and the Y is in the bending axis direction. And so this kind of compression with the tensile strain is consistent with the fact that molybdenum disulfide has this positive Poisson's ratio. So we can do this over a number of different nominal strains, and we find that the tensile strain in X increases while the compressive strain in Y has a tendency to decrease. And if we focus on the tensile strain, just the X direction, we find that the measured strain will increase as a function of the nominal strain. However, after 2%, we find values where the film seems to be completely relaxed. This, in addition to the fact that when we measure the tunneling spectra on each radii of curvature, despite the fact that the minimum value of the gap reduces monotonically as a function of the nominal strain, we still find areas that have seemingly the relaxed lattice constant. This indicates that there is likely, because this is a van der Waals material, as we're bending the sample, the film can slip with respect to the substrate and cause areas that, despite the fact that we are straining severely the substrate, we have a kind of a relaxed gap. But I'll talk more about that in the next couple slides. If we plot the measured atomic strain as a function of the gap on each one of those areas, we find a negative trend of about negative 320 MeV per percent strain, which is a little bit higher than what you'll find in the literature in measurements of the optical gap. However, it is a little bit lower than the recent measurement on moly sulfide in an in-plane heterojunction that took advantage of the lattice mismatch between tungsten cyanide and moly sulfide, where they see a reduction of about 500 MeV per percent strain. So with my remaining time, I just want to discuss this strain relaxation, wherein there were several optical papers that measured kind of a similar geometry, and they found that after a certain strain, they could find this so-called slipping. And the idea there is that if you're straining the substrate, the film will go with it to a certain point, but then, again, because it's weakly adhered to the substrate, it can slip back about the axis. So this has been also modeled using molecular dynamic simulations, and it's been seen that these ripple formations, these ripples can form as a result of this slipping. And indeed, this is what we see using STM. We found, in particular, an interesting situation here with two parallel ripples, atomic scale ripples, next to each other. And if we measure the atomic displacement, zooming in on the ripple on the right-hand side, we find this inhomogeneous kind of displacement of the atomic lattice that's in a direction that's kind of perpendicular to the direction of the ripple. We measure the tunneling spectroscopy as a function of position across this ripple from the left-hand side, which is close to the neighboring ripple, to the right-hand side. And we find a increase of the gap immediately at the site of the ripple of about 150 MeV. If we take a look at the conductance map at that valence band edge in real space, we can find that there's an abundance of states here that are localized in between the two ripples, but it falls off as you move away from the two ripples, which has interesting applications to strain engineering in this material. An additional relaxation that we found is related to defects, or otherwise where the film has an inhomogeneous adhesion to the substrate, causing slipping in some areas but not all areas. And this is displayed in STM by a moire pattern that can be visible in some locations but not all. And so if we look at one of these kind of bunched areas of the film, again we can look at the atomic displacement field, and it looks like there's a sharp change at this kind of wrinkling edge of the film. If we take the tunneling spectroscopy as a function of position, we find a mid-gap state highly localized around this defect. And on the moire lattice, we see a change in the band structure that's very localized as well. And in order to get a better view of this, we can take a conductance map, at this time at as a function of energy. And while we're in the gap here, of course, we don't see any states, but we would expect once we hit around -1 eV, we should see these highly localized in-gap states, which have the same, which are localized within about a nanometer on top of this defect. But the really interesting part of this is once the valence band edge comes in, we find that it takes on the shape of both the moire pattern that we see, as well as the displacement field, indicating that there's a very strong relationship here on the atomic scale between the strain field and the density of states of the semiconductor. So it looks like time's up. So I'll conclude by saying that we've found that the molybdenum disulfide has a reduction of the band gap with increasing thickness due to the overlap of the interfacial sulfur orbitals. In addition, we find that it is more the moire pattern and less the crystallographic orientation that dictates the change of the band gap with twisted heterostructures. And lastly, we found that this strain is a very strong tuning parameter, but also it's difficult to apply a reproducible strain on the material, as it has the tendency to slip. Thank you.
Thank you. Questions, comments?
I have a couple of technical questions.
Sure.
What is the temperature of the STM measurement? How you build the structure? And how you can control the angle between different elements?
Okay. So the first is the temperature of the STM measurements are done at 4 Kelvin at helium. The second one was how you build the structure. Did you mean the film on the substrate, or the
different material, for example, molybdenum with different layers, because you use MoS2, and in the top you put a graphene layer.
So it's just the opposite. We have the yes, and it's a graphite substrate, just a HOPG substrate that we deposit molysulfide on with a CVD. Yeah, and the last one was the yeah, sure. So the actual growth technique that we've done, it displays a random orientation of the film with respect to the substrate. So it was kind of a natural study.
Yeah, when you apply the low-layer Fujita algorithm, so you can, I mean, there are the atomic positions, which, by the way, on the first part you showed some average, right? Some average of the there. This is an average.
Yeah.
Because you could do that atomically resolved, right?
This is, each one of these data points is an atomic position.
It's an atomic.
Yes, and so we extract the strain by taking each atomic position and comparing where it should be.
But you average over the whole image.
In order to get the strain, yes, because
You could do that also at each point and obtain an image of the strain.
that's exactly right. And that's where these displacement fields come from. And
Yeah.
in principle, you should take the derivative to find the exact strain, but it's a little bit more messy, and I just wanted to show the displacement field. But you're right. We think that the strain, since it's macroscopically applied over our 15 by 15 nanometer image, it should be uniform if we're applying a strain correctly.
Okay. Any other questions or comments? If not, let's thank our speaker and previous speaker together.